Welcome. Today, we're going to solve a common type of calculus problem. Finding a function when you're given its derivative and a point it passes through. Our main goal is to learn how to recover the original function f of x from its derivative f prime of x. By the end of this video, you'll be able to find the complete equation of a curve using just its rate of change and 1 point. The problem asks us to find the equation of a curve, y equals f of x. We are given its derivative, which is f prime of x equals 1 over the square root of x, plus 6 over 6 to the power of x. And we are also given a condition, or a boundary condition, that the curve passes through the point where x is 3 and y is 1. This is written as f of 3 equals 1. So our task is to find f of x given f prime of x and the fact that f of 3 is 1. To find the original function f of x, we need to do the reverse operation of differentiation. This reverse operation is called integration. We find f of x by integrating f prime of x with respect to x. Remember, integration is the antiderivative. So let's set up our integral using the given derivative. F of x is equal to the integral of the quantity 1 over the square root of x, plus 6 over 6 to the x with respect to x. Before we can integrate, it's a good idea to rewrite our terms using exponents and to separate the integral into two parts, which is a property of integrals. The square root of x is x to the power of 1/2. In the denominator, it becomes x to the power of negative 1/2. The term 6 over 6 to the x can be written as 6 times 6 to the negative x, or simply 6 to the power of 1 minus x. We can now integrate each term separately. This gives us the integral of x to the negative 1/2 dx, plus the integral of 6 to the 1 minus x dx. Now, let's find the integral of each part. We'll start with the first term. We need to integrate x to the power of negative 1/2. This is a perfect candidate for the power rule of integration. The power rule says that to integrate x to the n, you add 1 to the power and divide by the new power. In our case, n is negative 1/2, so we apply the rule. We get x to the power of negative 1/2 plus 1, all divided by negative 1/2 plus 1. Negative 1/2 plus 1 is positive 1/2. Dividing by 1/2 is the same as multiplying by 2. And x to the 1/2 is the square root of x. So the integral of x to the negative 1/2 is 2 times the square root of x, plus a constant of integration. Now let's tackle the second term. We need to integrate 6 to the power of 1 minus x. This looks like an exponential function, but it's not a standard e to the x. We need a specific rule for integrating a number raised to a power. The general rule for the integral of a to the power of u, where a is a constant and u is a function of x, is a to the u divided by the natural logarithm of a times the derivative of u. However, if the derivative of u is not 1, we must perform a u substitution. Let's do that now. Let u equal the exponent, 1 minus x. Then the derivative of u with respect to x du dx is negative 1. This means du is equal to negative dx, or dx is equal to negative du. Now substitute these into our integral. We get the integral of 6 to the power of u times negative du. Now we can apply the rule directly. The integral is negative times 6 to the u divided by the natural logarithm of 6. Replacing u with 1 minus x, our final integral is negative 6 to the power of 1 minus x divided by the natural logarithm of 6. Great, we've integrated both terms. Now we can put them back together to get the general form of f of x. F of x is the sum of our two results. So f of x equals 2 root x minus 6 to the 1 minus x over the natural log of 6. Now you might be wondering about the constants of integration. What happened to c1 and c2? When we add two unknown constants, c1 and c2, we just get another unknown constant. It's standard practice to combine them into a single constant, which we usually call c. So our general solution for the function f of x is 2 root x minus 6 to the 1 minus x over the natural log of 6 plus c. This c is an unknown constant. Our last step is to find the value of this constant c. This is where we use the initial condition that was given. The problem states that fe of 3 equals 1. This means when we plug in x equals 3 into our function, the output must be 1. Let's substitute x equals 3 into the equation we just found. We get 1 equals 2 root 3 minus 6 to the power of 1 minus 3, all divided by the natural log of 6 plus c. Now we just need to simplify and solve for c. The exponent 1 minus 3 is negative 2, so we have 1 equals 2 root 3 minus 6 to the negative 2 over the natural log of 6 plus c. Since 6 to the negative 2 is 1 over 6 squared, which is 1 over 36, our equation is 1 equals 2 root 3 minus 1 over 36 times the natural log of 6 plus c. To find c, we simply rearrange the equation by subtracting the other terms from 1. This gives us c equals 1 minus 2 root 3 plus 1 over 36 times the natural log of 6. This might look complicated, but it's just a number. It's our constant. We're almost there. We have our general solution for f of x, and we have the exact value of our constant c. The general solution was f of x equals 2 root x minus 6 to the 1 minus x over ln of 6 plus c. And our constant was c equals 1 minus 2 root 3 plus 1 over 36 ln of 6. The final step is to substitute this specific value of c back into our general function. This will give us the specific function that not only has the correct derivative, but also passes through the point 3, 1. Substituting c back in, we get that f of x equals 2 root x minus 6 to the 1 minus x over ln of 6 plus 1 minus 2 root 3 plus 1 over 36 ln of 6. This is our final answer. We have successfully recovered the original function from its derivative and a given point. To recap, we integrated the derivative term by term, which resulted in a function plus an unknown constant. We then used the initial condition f of 3 equals 1 to form an equation and solve for that constant. Finally, we substituted the constant back in to get the unique solution. Let's quickly verify our answer by differentiating it to see if we get back the original f prime of x. This is an excellent way to check your work. Remember, our answer is f of x equals 2 root x minus 6 to the 1 minus x over ln of 6 plus c, where c is our constant. Let's differentiate each term. The derivative of a constant is 0, so the entire constant part at the end disappears. The derivative of 2 root x, or 2 times x to the 1/2, is 2 times 1/2 times x to the negative 1/2, which simplifies to x to the negative 1/2, or 1 over root x. This matches the first term of f prime of x. For the second term, we differentiate negative 6 to the 1 minus x divided by ln of 6. The ln of 6 is just a constant in the denominator. We use the exponential rule. The derivative of 6 to the 1 minus x is 6 to the 1 minus x times ln of 6 times the derivative of the exponent, which is negative 1. The negative from this term cancels the negative outside the fraction. The ln of 6 in the numerator and denominator cancel out. We are left with 6 to the power of 1 minus x, which is exactly 6 divided by 6 to the x. Since both terms match, our solution is correct. We have successfully found the specific function f of x that satisfies both the given derivative and the given point. Let's quickly summarize what we accomplished today. We started with a learning goal, to recover an original function from its derivative and a point. We achieved this by following a 3-step process. First, we integrated the given derivative term by term. This gave us a family of functions, each differing by an arbitrary constant c. Second, we used the provided initial condition, f of 3 equals 1, to create an equation that allowed us to find the exact value of our constant c. Finally, we substituted this specific value of c back into our general solution. This yielded the unique function f of x that satisfies both conditions. You now have the tools to solve similar problems. Thank you for watching.